3 doors, behind one of them a car. Behind the other 2, goats. You pick a door, say number 1. The host, who knows what's behind every door, opens another, say number 3, revealing a goat. Then he offers you a choice: stick with your door or switch to the last one. Most people say it makes no difference. 2 doors left, 50-50, it feels obvious. It's also wrong. Switching doesn't just help, it doubles your chance of winning. Today, we'll prove it 4 different ways and see exactly why our intuition betrays us. First, the rules, because here they are everything. There are 3 doors. The car is placed at random. You make your first pick blind. Then comes the crucial part. The host always knows where the car is. He always opens a door you did not pick. And he always reveals a goat, never the car. When 2 goats are his to choose from, he opens one at random. Finally, he always offers the switch. Hold these rules in mind. Change any one of them, and the answer changes too. We'll come back to that in detail. Here's the trap. After the host opens a goat door, 2 doors remain. One hides the car. So the odds are 50-50, right? Switching can't matter. That feels airtight, but it quietly assumes the 2 remaining doors are equal. They are not. To see why, go back to the moment you first chose. Before I show you, try it yourself. You've picked door 1. The host has opened door 3, a goat. Should you stay or switch? Trust your gut for a moment. Hold that answer. Most people feel it can't possibly matter. Let's find out, slowly and carefully. When you first picked, you had a 1 in 3 chance of being right, which means 2 times out of 3, the car was behind one of the other doors. That first probability doesn't change just because a door swings open. Your door was, and stays, 1 in 3. So the other 2 doors together must hold the remaining 2 in 3. Now the host helpfully removes one of those other doors, always a goat. He never touches your door. So all of that 2 in 3 weight collapses onto the single door he leaves closed. Your door, 1 in 3. The other door, 2 in 3. Switching wins twice as often. Let's prove it by listing every case. Say the car is behind door 1. Pick door 1 and switch, you lose. Pick door 2, the host must open 3, you switch to 1, you win. Pick door 3, you switch, you win. 2 wins out of 3 by switching. And the same pattern holds wherever the car is. If you've met Bayes' theorem, here's the very same answer in its language. It's a recipe for updating a belief the instant new evidence arrives. Before the host moves, the car is equally likely behind any door, 1/3 each. That's your prior. You picked door 1 and the host opened door 3. Now ask, how likely was the host to open door 3 in each world? If the car is behind your door 1, he could open 2 or 3 freely, so he picks 3 about half the time. But if the car is behind door 2, the host is forced. He can't open your door and he can't reveal the car, so he must open 3 every single time. Bayes weighs these. The forced world, car behind door 2, is twice as consistent with what you actually saw. So the probability the car sits behind door 2 updates to 2/3. Same answer, now proven with arithmetic. Still feels strange? Scale it up. Imagine not 3 doors but 100. 1 car, 99 goats, you pick a single door. Your chance of being right? 1 in 100. Almost certainly, the car is somewhere among the other 99. Now the host, who knows, opens 98 doors, every single one a goat, leaving just your door and one other. Would you switch? Of course you would. Your door was a 1 in 100 guess. The other door has soaked up the other 99. The host has all but pointed at the car. 3 doors is the very same thing, just harder to feel. The host's knowledge is the whole trick. And that's the real lesson. The host isn't opening a random door. He's acting on information you don't have and leaking some of it to you. If a door had simply blown open in the wind and happened to show a goat, that would tell you nothing, and the odds really would be 50-50. But a knowing host, bound to reveal a goat, always concentrates the odds onto the door he refuses to open. Information has weight. Don't trust the argument, let a computer settle it, but first, watch a few rounds, one at a time. Round 1, the car's behind door 2. You pick one. The host opens 3, you switch and you win. Round 2, car behind door 1, you pick 1, switch away and you lose. Round 3, you switch and win again. 2 wins in 3 rounds just by switching. Now let the machine play thousands of games, 2 ways, always stick and always switch. Watch the win rate settle. Sticking hovers near 33%, switching climbs toward 67%. No theory, just tallies. The 2/3 is real, and it shows up every time you run it. The whole result hangs on the host's rules. Loosen them and watch the answer move. Version 1, a forgetful host who doesn't know where the car is and opens a random door that just happens to show a goat. Now switching wins only half the time. The lucky reveal carried no information. Version 2, a mischievous host who offers a switch only when you've already picked the car. Take that generous-looking offer and you lose every time. Here, reading his intent matters more than any formula. Same 3 doors, wildly different odds, depending only on what the host is required to do. The paradox was never really about the doors. The puzzle takes its name from a real show. Through the 1960s and 70s, Monty Hall hosted Let's Make a Deal, where contestants traded and gambled for prizes hidden behind curtains and doors, or for booby prizes they called zonks. But the puzzle truly exploded in 1990, when a columnist named Marilyn Vos Savant gave the correct answer, switch, in a magazine. Thousands of readers wrote in to say she was wrong. Many held PhDs. Some were mathematicians, scolding her in print. She was right, and they were not. Even Paul Erdos, one of the most brilliant mathematicians of the century, refused to believe it until his friend Andrew Vasiny showed him a computer simulation. The wrong intuition is that powerful. And remember the rules. The 2/3 only holds because the host knows and is bound to reveal a goat and always offers the switch. If the host could open the car, or only offered a switch when you'd already picked right, the math would flip. The paradox lives entirely in what the host is forced to do. So why does our intuition fail so badly? Because the moment a door opens, we treat what's left as a brand new, fair choice, forgetting the history that made the 2 doors unequal. Our minds reach for symmetry. 2 doors, so 50-50. We quietly ignore that one of them survived a filter the host was forced to apply, while our own door never faced that test. That blind spot, mistaking a loaded situation for a fair coin, reaches far beyond game shows, into medicine, courtrooms, and the news. Learning to feel the difference is a quietly powerful skill. So the next time your gut says 50-50, pause. Ask what the other side knows and what their choice just told you. 3 doors, 1 goat revealed, and a quiet doubling of your odds, hiding in plain sight all along.